Hello everyone, welcome back to this lab session. Today I will discuss about a simple MATLAB code for generating sampled signal of the analog sinusoidal waveform. So here, if you observe this code, here we are taking the input signal as a sinusoidal signal and an analog signal, and let us see how this analog sinusoidal signal is going to be converted into sampled signal. And in that sample signal, we are going to verify what are the different conditions of sampling, and also we are going to verify the sampling condition and all the outputs of the sample signal for different conditions of sampling, like undersampling, oversampling, and critically sampling, etc. Now, here, as you all know that the sampling is nothing but just it will generate a discrete time signal of the original analog signal. For example, if you take a sinusoidal signal, the discrete version of that signal in time domain will be displayed as a samples. So each sample will be displayed as a is like a delta function, okay, or one impulse for every sampling time interval. Now, let us see how you are considering the input signal and how the sample signal is obtained. Here, let us observe this. The first thing, I am taking one sampling frequency as 500 into 10 power cube, that is 500 kilohertz. So the notation, that is 500 E3, which is equal to 500 into 10 power cube. That means, let us considering a sampling frequency which is 500 kilohertz, which is a very high sampling rate. So why this is used? In order to proper display of the signal. For example, if you want to display any signal in MATLAB, any sinusoidal signal or any analog signal in MATLAB, so the main function is we need to plot that signal as like this, that is plot of t comma x, that is plot time x-axis, which is a time, and y-axis there is amplitude. So you should write like plot of x-axis parameter comma y-axis parameter. So here for a sinusoidal signal which is depending on time, that is a time domain signal, so plot of t comma x, where x is equal to sine of 2 pi fct or 2 pi ft simply. Okay. So, in order to display this plot of this sinusoidal signal, you must represent the time axis of the sinusoidal signal before displaying it. Here, what is the t? Generally, the t should be represented as like this notation, starting from 0 and varied in the interval to the last value. This is what the general representation. Okay. So just I am clarifying you like this. So time axis of that sinusoidal signal will vary from 0 to 100 in the interval of 0.1. That means for each interval, the time axis is varied from 0, 0.1, 0.2, 0.3, 0.4, and so on up to 100. Many time references or time intervals are there in the input signal time axis. So this must be selected based on the frequency of the input signal, based on the frequency of the input signal and how many number of cycles we need to have. For example, here in our case, we are considering the practical values of sinusoidal frequencies. Okay, but in general, in any MATLAB examples, generally we take f is equal to 100 or f is equal to 10 like that. But in practical uses, generally frequency values of any voice signals or any audio signals or maybe any other electromagnetic signals are having some frequencies in terms of kilohertz, 10 kilohertz, 30 kilohertz, 40 kilohertz, 100 kilohertz, something like that. So that's why, since the frequency of the input signal, frequency of the input sinusoidal signal is considering as 10 into 10 cube, that is 10 kilohertz. This is what 10 kilohertz of input signal frequency. So let us consider 10 kilohertz is the input signal frequency. Let us take that as f. So since signal frequency is 10 into 10 cube, that is 10,000 units. So based on the 10,000 units, we need to divide the time axis as if it is 0 to 100, you may take 0.1. If it is 0 to 10,000 like this, 0 to 10,000 like this, okay, it is more than like this, then this interval must be very, very small like this. That's why, in order to represent like this, here I am taking a notation that, so let us consider n equal to 5, that is the number of cycles we need to generate in the output. You can take this any number. Suppose, for example, here I am taking 5 cycles to display in the waveform. So the time axis is represented as, it is starting from 0 like this, and ending value, the last value is like this, that is n by f, n into 1 by f. That means number of cycles, that is 5, by the frequency of the input signal, that is 10 kilohertz or 10 into 10 cube. See here, why I am taking this 5 by 10 into 10 cube means we need to restrict the total number of cycles of the sinusoidal waveform within 5 cycles only. That's why we need to divide this 5 by, that is n by f. And how this is changed in the interval space must be as low as possible in order to perfectly display the sinusoidal waveform. So that's why that is selected as 1 by fs, where fs is taken as 500 into 10 cube, which is very high. So 1 by this 500 into 10 cube is very, very less. So if you take this time interval as low as possible, then we can able to perfectly display the sinusoidal signal. For example, if you observe this, if you plot this waveform, for example, here I am commenting the remaining code and try to observe only that one. Okay, here I am going to observe only this input sinusoidal signal, that is plot of t comma x. So I am giving the title as sinusoidal signal, x axis time, y axis amplitude. So let me display this. This is what the sinusoidal signal, amplitude, time, continuous sinusoidal signal as the input signal, and the x-axis is in the range of some value, that is 6 or 5 into 10 power minus 4, because we have taken that 1 by fs, that is in terms of millisecond or microsecond. Next, why you need to understand why I am taking this interval as low as possible and this frequency as high as possible. For example, I am reducing this frequency up to 100. Then this will be also be increased. This is reduced, the time interval is going to be increased. Then you may not observe the perfect sinusoidal waveform. You can observe this. Clearly there will be some disturbances, right? This is not a perfect sinusoidal waveform. Similarly, if you reduce that up to 80, next, let us observe this. Again there will be some disturbance. If you reduce that to 50, then you can clearly observe there is a disturbance. So the sinusoidal waveform cannot be displayed perfectly if you don't select that time interval in the time axis as low as possible, depending on the maximum value of the frequency, right? So that's why I am taking this as high as possible. Even if you select this 1000 also, it will be perfect. It will be perfect sinusoidal wave. So that's why select this time interval as low as possible, so that that inverse, that is frequency, must be as high as possible. So that is all about displaying the input signal waveform by using plot function based on x is equal to the input signal, that is sine of 2 pi ft, and t is the time axis, which must be represented from lower limit to higher limit, based on this time interval. This time interval is selected based on this particular frequency. Okay. Anyway, we will change that sampling frequency later in order to observe different conditions. Now, let me uncomment this enter thing. Let us observe. Now, let us see the next version, next portion of the code. FS1. Here I am going to change the sampling frequency. FS1 is equal to 40 into 10 cube. 40 cube means 40 into 10 cube, that is nothing but 40 kilohertz sampling rate is selected. And again, to display the sampling frequency, again we need to change the time of this waveform. Okay, time and x, both these must be changed. So T for this particular sample signal is taken as T1 is equal to, again the same notation, 0, 1 by Fs. So here 1 by Fs1, n by F, here also n by F. Next, display that sinusoidal signal again based on this time axis, that is x1 is equal to sin 2 pi f t1. Next, again similarly take another sampling frequency. So let us take fs2 is equal to 300 cube. 300 kilohertz is very high sampling rate. In that condition, we can take it as a oversample. Now again, the time axis is represented in a similar way: 0, 1 by fs2, n by f, and x2 is equal to sin of 2 pi f t2. Now I am going to display this input signal, sample signal in this first case, sample signal in the second case, all these three in a single window. So we need to take that as subplot of 3, 1, 1. That means 3, 1 represents, it is a 3 by 1 matrix. That means 3 rows in 3 elements in single column. That means 3 different graphs will be displayed in a single column. So 3, 1, 1 is the first graph, 3, 1, 2 is the second graph, 3, 1, 3 is the third graph. So first graph we are going to display the input signal, and second graph we need to display the x1. What is x1? Sample signal 1. So again title and y-axis axis are same. And if you press this hold on, that means initially we are displaying this plot t, x, that is input signal is displayed. If you type hold on, that means on the input signal, this stem, what is the meaning of stem? Means we display stem, then the samples are the impulses of that particular analog signal will be displayed directly based on this time axis. Okay, so whenever you need to display the sample signal, you must use this function, that is stem, in order to display the sample signal. So here, if a hold on is inserted here, then both the sample signal or input signal both are combined and displayed just as per a comparison. And similarly, the third graph along with input signal, second sample signal is displayed. Now let us see the output finally. I'm running this directly. Now clearly observe all of you. This is what continuous input signal having 5 cycles, because we have selected 5 cycles. Now this is what the sampled signal. So these brown color impulses, you can clearly observe, these are the samples. These are the samples corresponding to this blue color input line. Because if you write the code with the statement hold on, then along with the input these samples will be displayed. If you remove that, only this sample signal is only displayed. So this is sample signal 1 for 30 kHz of sampling frequency, and this is the sample signal 2 with 400 kHz of sampling frequency, that is very high. So during this condition, you can say that this is a oversampled signal. For example, let us change the sampling frequency to different values and try to observe what will be the sample signals. Okay. Now, so in the second case, let us change the sampling frequency fs1 to, for example, here I am taking 5 kHz. Okay, so it is 5 kHz. Now, what is this? If the sampling frequency is 5 kHz and the input signal frequency is 10 kHz, that means we can clearly observe that Fs is less than 2 FM. So we can clearly say that it is a undersampling frequency. It is a undersampling frequency. So you can give the title for sample signal 1 as undersampled. Undersampled. Next, second signal frequency. Second sample frequency is selected as 300 kHz. So always it is 4 sampling frequency because Fs is very high compared to TM. 300 kHz is very high compared to 2 times FM, that is 20 kHz. Now let us title this as oversampled. Now let us observe the outputs. So this is the undersampled signal of this input signal. So we clearly observe that this is what the input signal. This is one sample. This is the second sample. This is third sample. So for this entire input signal, only 3 samples are obtained. So that is very undersampled signal. Similarly, if you observe the oversampled signal, then many number of samples are obtained. Many number of samples are obtained for this oversampled signal. Okay. So what is our condition? In order to perfectly reconstruct the sample signal, the sampling frequency must be very high or just greater than 2 FM, at least greater than 2 FM. If it is Fs is very much greater than 2 FM, then we can perfectly reconstruct the original signal. So based on this sample signal, if you want to reconstruct this into original signal, then the sampling rate must be as high as possible, like this. Because if you want to reconstruct this undersampled signal to original signal, then it is very difficult and you cannot able to reconstruct the signal because only 2 samples are there, 3 samples are there. So based on these 3 samples, we cannot able to reconstruct this into original signal. For example, let us change some value like undersampling case as 10 kHz. So this is Fs is equal to 10 kHz and Fm is equal to again 10 kHz. So Fs is 10 kHz, which is less than 2 times Fm. 2 times Fm is 20 kHz. So again this is considered as an undersampled case. So again if you observe that there will be some samples which are very less in order to reconstruct this original signal. So this is what the different conditions of sampling. And also we have already verified that sampling condition. So in order to perfectly reconstruct the original signal, the sampling rate must be higher than 2 times the input signal frequency. Here input signal frequency 20 kHz, 10 kHz. So 2 times of input signal frequency is 20 kHz. So whatever the sampling frequency you are selecting, that must be greater than 20 kHz. So this is the case, it is very high compared to 20 kHz. Only in this case only you can able to get the perfect reconstruction. Okay. So that's it for the lab session. Okay. Thank you very much.